Well, he had songs after that, but sort of his later ones from the 70s. Okay, guys. So the green sheet is our outline, yeah, and you see we're doing alkene oxidation. So this is described here. Everything we're doing there. The pink is sort of outlined, and we're looking at oxidation of alkenes. Things are there. The blue is sort of the written stuff, which for me used to be on the board, but now I put it, over the years I put more and more on handouts like this. And so we're doing some oxidation of alkenes. And so one of the first ones is the KMNO4. What does KMNO4 do to an alkene? Synaddition to give a
diol.
Yeah, I want to this one diol. Synaddition, a cis product. Okay. Importantly, though, as we'll see later, KMNO4 has to be done in mild conditions. If you heat it too much, you'll get a different outcome. We'll see that in a couple of more pages. So it's a little finicky. To get a better yield of that, we can use another oxidizer, and that's what?
Is it the osmium tetroxide?
Osmium tetroxide, yes. If you check your periodic table, the osmium is sort of just to the side of manganese. Manganese is MnO4 manganese, not magnesium. Yeah. Okay. But osmium is a little bit toxic. All right. But if you want a better yield, you know, it might be that's what you want to do. With the osmium, the ester is stable. We have to come in with sort of a magic step. I call it magic because we didn't look at the details. All right. That's just my sort of, just call it magic. We can cleave the osmate ester and get the diol there. But importantly, yes, synaddition. Guaifenesin and a lot of decongestants. If you look at the bottle, like purple decongestants, does have a diol there. And so that could come from precursor. Makes sense? We had that alkene. We reacted these reagents to give that diol. Yeah, there you go. And this is one way how you can make guaifenesin. And it, you know, there's other oxidants that will do this. I doubt they're using on commercial osmium tetroxide on commercial scale. How would you make this? We can go back just to do that. How could you back this up? Well, one way to back it up is to go back to this guy. Okay? If you had this, how would you make that?
Williamson ether synthesis?
Yes. React this first with like sodium hydroxide to make the anion, and then come in with what? They look a little strange, but
With a leaving group, yeah.
that's a chlorine. That right there? Oxygen kicks off the chlorine, make that bond? Yeah. What's the name of this fragment right here? Because that's something chloride. I know that. Not vinyl. Vinyl chloride is just the alkene. That's vinyl chloride. This has a CH2 between it. Anybody remember this? Allylic. Benzylic and allylic, okay? Allylic chloride, or it's called allyl chloride. Allyl chloride is very common. So you do a Weisman ether synthesis with allyl chloride, coming from this. This is a phenol with a methoxy. We will learn aromatic nomenclature. This is, officially it's 2-methoxyphenol. Okay, phenol, 2-methoxy, 2. Common name is guaiacol. You don't need to know this, but the only reason I say it is because guaiacol is used to make guafenicin. That's just where that gua comes from. Guaiacol. Okay? But you see the Williamson ether synthesis, and then you can do your oxidation of your alkene to give the diol out there. Alright? Where this is probably, you're just going to buy that. I mean, something, you start with something. And how is that made? Well, there's a lot of things that are made commercially that are made by very strange methods that are beyond the scope of our class, because there's lots of chemistry out there. This may also be a natural product, maybe. Or it may come from the diol here, and they just selectively monomethylate it. But, okay, we're not going to go all the way back to carbon. All right, you usually start with something, right? Just like when you bake, you know, you may buy your flour, or you may make your flour. You buy your sugar. Nobody's making sugar, are they? Everybody usually buys it. Some things you just buy, and you may never ask, well, how do you make the sugar? Well, okay, down here, stereochemistry. Stereochemistry. Show product in the Fisher projection. Remember Fisher? You guys did Fisher in Organic 1, everybody? Yeah? We did some Fisher projection?
Oh, yes.
A little bit? First thing, you know, what type of product are we making here? I already said that, right? Decimal. Okay, so that's your prompt. You got a little bit of memorization. You got to know your reactions. Okay? And then your knowledge comes in. Let's see, and I recommended in Organic 1, probably you other guys didn't see this, but my recommendation is what?
Draw the...
Because this is one of these types where both carbons are going to be chiral in the product. And that's where we really have to look at it. Turn your alkene, all right? Turn it. Right now it's like this. All right? Thumb down, 2 fingers up. Turn it like this, so that this group is forward. Or you can turn it the other way. But now the methyl, let's just show it forward and put the phenyl back. And put the methyl back. Okay? That's just me turning it. I can draw my hand on the board with the thumb down. But we also need to be able to envision the hand on the board like this and the thumb coming out. Okay? Pinky up, thumb down. But if I turn it like this, now the thumb's forward and the pinky's back. That's all I've done here. That's very powerful because now we have projections which we can keep. And it makes your life a lot easier if you want to learn how to do this. Now, we don't have to go through full mechanism. What do we know about this outcome?
Syn addition.
Syn addition. Both OHs straight up or straight down. We can put the new things in the plane. Okay? Now we got our alkene like this. Straight down or straight up, because the alkene has 2 faces. The reagent can attack from the top or the bottom. Get rid of the pi bond and draw the OHs straight down. New things straight up or straight down in the plane. Now this bond looks a little ugly here. You can erase it and make it a little better. This is going to be, it's tetrahedral. This is going to project up a little bit. You know, we can draw it sort of up a little bit, but it's still forward. But now it may look a little better. We had it before, but it just looks better now. Right? But we also are going to have the other, where, again, the start is the same. Okay? Get rid of the pi bond and draw them both up. And those are your two products. What's the relationship between those two on the board? Yeah, they're enantiomers. You see that? Because if that's a mirror plane, they're mirroring each other. Again, depending on how this is actually drawn, but it's two. Okay, phenyls are both back, methyls are both forward. OH going away, OH going away. Hopefully, see those are mirror images. You get mirror images by attack from the top and the bottom. Okay? Show product in a fissure. Well, you don't have to show both. I mean, you can clarify the question. But put this in a fissure. Does it give you any? It doesn't give you any directions. What's at top or bottom? Typically, carbon groups at top and bottom, and non-carbons on the sides in fissure. Okay, let's put the phenyl at the top. If phenyl's going to be at the top, that means this is the ground. If that's the ground, I'm going to stand on the ground. I usually do. You guys do too. And let's look through here. Why am I on this side? I'm on that side so that this OH can be going straight away. If the OH is going away, what side is the phenyl on?
Right.
Right.
The OH is going away, the phenyl is on the right. But I'm up here looking at it. Okay? The phenyl's going behind the board to our right. The methyl is coming this way. Here I am on the ground. Or we can take all this and hold it up. It's just fell over and I'm hovering up here. With the OH going away, the methyl's on the left. I'll draw that as an ME. Okay, with this OH going away, just bend your knees a little bit, shrink down and look through here. With the OH going away, this methyl is on my
Right.
side.
correct. Methyl's on the right, OH going away. What's on the left?
Hydrogen.
I'm drawing hydrogen. Good. There you go. That's in a Fisher projection. But erythro-3O, typically, you need to have substituents on sides. We can rotate this here. It doesn't matter. Let's put the phenyl at the top. No, let's do this. Again, here it doesn't matter. I'll put methyls at top and bottom. That means methyl down here, methyl up here. If we rotate this, the methyl moves to the top, the OH is going to be here, and the phenyl will be here. Methyl down here, the OH will move here, and the H here. If the direction said methyl at top and bottom, would it be erythro or 3O? Be 3O. Did you guys see erythro and 3O in organic 1? Or did not have me? Did you guys see erythro 3O?
No, sir.
No? Did you do up to this point?
Yes.
Okay. Well, this is just diastereomer term.
Oh.
Each carbon here, what's high priority on this carbon? O or carbon?
No.
O, down here, O. When high priority groups are on opposite sides in your fissure, that's 3O. If high priority groups are on the same side in your fissure, it's erythro. Okay? Remember that because, okay, this starts with an E. If you draw a capital E, your horizontal lines of the E are on the same side. But if you draw a capital T, which is here and then here, you've got lines on both sides. That's how I remember it. This came from 4-carbon sugars. Are they 4 carbons? You'll have to look at that. I think it's 4 carbons. And if you look at carbohydrates, now glucose is a 6-carbon sugar, but if you look at the 4-carbon sugars, I don't know if that's right or not. It may be 2 or 3 carbons. But if you look at those, there's 2 isomers at that level, and they're called erythros and threose. And it's because the OH groups are either on the same side or opposite. And that's where this terminology comes from. And so this reaction is going to give 3O plus an enantiomer. What will the enantiomer look like? Will the enantiomer be 3O or erythro?
It'd be 3O.
Rhea.
It will also be 3O. Because if you draw the enantiomer, it's just going to be the same thing, just all inverted. Yeah, plus an enantiomer. You're only going to get 3O plus an enantiomer. You should be able to just draw the enantiomer of that. The product is 3O here. And so you should be able to answer these types of questions for your stereochemistry, putting together your mechanistic knowledge and reaction outcome, doing Fisher projections, and then erythro 3O is just terminology so you can tell someone what you got instead of having to show it. If you didn't have terminology, how would you explain what you get? You'd have to say, hey, let me show you. Terminology allows us to speak more succinctly about what we got. Okay, I expect you to know most of that from Organic 1. The new part is, of course, our reaction. We have a new reaction, a syn
Addition.
dihydroxylation. But then take it from there from a lot of your knowledge from Organic 1. Yeah, magic steps, it's your outcome. Questions? There's carbohydrates. If you look up a list of carbohydrates, you'll see the different ones. 2 carbons, 3 carbons, 4 carbons, 5 carbons, and 6 carbons where glucose falls. Glucose and mannose and all those. Okay. Now diols, there's a reaction you can do with them. Diols can be cleaved, okay? The 2 carbons there can be cleaved, and each carbon becomes double bonded to the other. Oxidative cleavage of bisphenol diols. Now, reagents that can do this is periodic acid. HiO4, fairly common oxidant, although it's more common to have the sodium salt. Sodium periodate. Because the acid is a little unstable, it's liquid and stuff. Sodium periodate is a nice solid. And it you can just use it and acid, and it'll just generate this. Similar structure to like osmium tetroxide, et cetera, et cetera. Iodine here typically makes 1 bond, right? Halogen. But of course, once you get below the second row, these guys down here can actually make additional bonds beyond typical. I mean, oxygen 2 bonds, sulfur 2 bonds. But we also see sulfur with 4 bonds and more, because it has d orbitals and it can expand its octet. Well, this is just iodine expanding its octet. Okay, so it's a unique bonding, but it is possible. The iodine is very oxidized. It's fully oxidized. The iodine has an oxidation state of +7 there. Okay? It has 7 bonds to oxygen. And that's fully oxidized because the iodine is group 7. Okay? But it's a very similar. The OH is kind of attack here, and you get back to sort of a 5-membered ring. But at this point, this thing will break down this way. And one of the most important things on this page is just, do you understand the arrow movement here? Because understanding your mechanistic arrow movement, these electrons move here, breaking the carbon-carbon sigma bond and moving here to make double bond between the C and the O. These electrons are moving. There's 2 long pairs there anyway, but those electrons move onto iodine. These electrons fall in here, and here's your double bond on this side between C and the O. And that actually gives these 2 products. Now when that becomes carbonyl, you have 2 methyls. So that's a ketone. When this becomes carbonyl, you have 1 methyl, and the other is an H here, right? There's an H there. It's still there. I drew it in, but that's an aldehyde. So these reactions can give either ketones or aldehydes depending on what's on this carbon. What's the fate of the iodine reactant here? It's this. Where did the lone pair come from? Well, that arrow right there, right? Everything's here. But the oxidation state now is +5. So the iodine has been reduced. What's been oxidized? Well, the 2 carbons have, because this carbon has 1 bond to a more electronegative atom. Now it has 2. So it is an oxidation of the carbons. It's called an oxidative cleavage, because we are cleaving the carbons as well. Okay? It's a type of pericyclic reaction, which means it involves a cyclic transition state. I'm not sure if chapter 29 refers to Klein. I may refer to a previous textbook, but I think Klein does have a dedicated chapter on pericyclic reactions, which is where you're going to find your Diels-Alder reaction. Okay? So, again, a little bit, just predict the product. Periodate is going to cleave. Doesn't matter if there's a sodium sitting out there instead of an H. Basically, a little bit of sort of predictive product, a little memorization. What does this do? It's going to cleave the 2 carbons. That becomes carbonyl. That becomes double bonded to that O. This becomes double bonded to the O. Does everybody agree that that's the product? Now in this case, it's only 1 molecule because it was connected through the original ring. And so we didn't cleave into 2 molecules, but we did cleave the ring, opened up the ring. There's an H on the top carbon, so the top carbon is actually now aldehyde. Can I see this? Okay. What about this? We can get that same product. All this is combining our 2 reactions. Can you convert an alkene to a cis-diol?
Yes.
That's what we just did with the Fisher. What will do that?
I was waiting to try to say.
Followed by a magic step.
Mm-hmm.
Yeah. Osmium, followed by the magic step. What are possible magic steps? Okay. This is just going to be syn dihydroxylation, right? So that's going to convert, make this. Then if you come in with this, what does this do to this diol product? Cleaves it. So can you see that if you start with this and do these here that you get this product? That's just combining 2 steps. Now I call it 2 steps. It's 3 reactions. But the 1 and 2 is sort of a one transformation. I call it one step. It's one synthetic conversion. Okay? So I just sort of combine things, and we... Ultimately, what did we do here? We went from an alkene, we cleaved the alkene. And each carbon became carbonyl. The reason that's important is because the next reaction does that. And the next reaction is one of the top 10s in organic chemistry. Now, you guys from other instructors of Organic 1 saw this. Ozonolysis? Yes. Ozonolysis will do this here, sort of all in one step. Let's look at ozonolysis. Now, ozonolysis is with ozone, O3. Okay? Let's see. Lewis structure may be like this. That seems to be a reasonable structure for ozone, O3. Ozone exists in the atmosphere. It's a strong absorber of UV. So it protects us from getting so much UV. But the ozone layer can be depleted and we get more UV. Ozone is generated it's also generated from oxygen by UV, so it's both generated and, okay, there's lots of chemistry there. You guys have seen ozone being generated before, most likely. You ever unplug something real fast and a little blue spark? That's ozone being generated. Electricity reacting with the oxygen. There's a little bit of flow of electricity as you unplug it, and it's reacting with the oxygen, generating ozone. Okay? Which is bluish. And there's a procedure in one of the handouts which maybe talks about the color and using ozone. Okay? But anyway, it's ozone, and so the reaction is called an ozonolysis. What does lysis mean? Lysis with cells in biology? What does that do? Breaks it, or okay, lysis. Cleaving. Yeah. You're cleaving the alkene with ozone. It's called an ozonolysis. Okay? It's what we did here, but it's, okay? It's ozone followed by a magic step. The magic step can either be zinc metal, just metal, or dimethyl sulfide. Also, like the magic steps up here, you can that's a reducing agent. No. They both may, no, that's got to be a reducing agent. Well, this is too. Okay, they're both reducing agents here. We'll see the chemistry. Let's look at ozonolysis. So you take an alkene, you do ozonolysis. What do we get? Transformation. We cleave the alkene. Each carbon becomes what? Carbonyl. And that's what we have over there. Each carbon is now bonded to an oxygen. This carbon has an H. And so the carbonyl carbon has an H, and that's an aldehyde. That carbon has two methyls. Okay? Under my hand is oxygen. That's what it becomes. All right? These two carbons used to be double bonded to each other as an alkene. Now we've cleaved them, and they're each now double bonded to oxygen. This is actually a very common way to make carbonyl compounds from alkenes.
Does ozone do this in a better yield than what we used previously in the last example?
Yes. I would say better yield, mainly because it's such a huge, important reaction. It must be a great reaction. I've never actually done one. But yeah, if it gave terrible yields, it wouldn't be so an important reaction. Okay, let's look at this mechanism. Ozone. Here, we could show a resonance structure of this structure. Looks like this. Now, remember we said this oxygen will hunt you down in organic 1. Why? No octet. So that's not a great resonance structure. This is much better. Octet here. Everything has octet here. The main reason I drew that is so we can sort of see it's a 3 plus 2. And 3 plus 2 is 5. Thank you. But look at this. Go back to this alkene chemistry. Remember alkenes attacking like H plus or C plus?
Mm-hmm.
You can imagine this attacking this. But it's concerted. When this attacks here, we're making a bond here. What do we generate over here? And we hit in organic 1, I said NAF. Carbocation?
Yeah.
But see, as soon as a carbocation is generated here, this negative oxygen is attacking here. And I'm just going to do it all concerted and not actually, there's no carbocation. But I'm envisioning one. But then boom, this is attacking it. And we get, it's a concerted, and that's going to make this 5-membered ring, carbon bonded to oxygen, and then oxygen bonded to carbon. This is called a malozonide, and it's unstable. It will break down. These electrons come here to make double bond between C and the O. These move over here to make double bond between C and the O. And these move off. And all that gives what? You might think it's the end product, but it's not. It gives these two. That actually becomes a carbonyl compound. But this is a very interesting carbonyl oxide. Again, it's important. How did this become 3 lone pairs? Well, the arrow is right there, moving the bond onto the oxygen as a lone pair, right? And of course, if it's got 3 lone pairs, it's minus. So your arrows are here. This is probably driven by the fact that oxygen doesn't like to bond to each other. I mean, this is a very reactive molecule, formed by electricity or intense UV light. We can form very reactive things. We just formed this very reactive ring here, but this is probably driven by breaking these oxygen bonds. One of them got broken, carbonyl oxide. These two then come back and react. This is carbonyl chemistry. You have dipole, partial positive. This attacks here, electrons up. I've just turned it over. This attacked here, electrons up onto oxygen. Then this guy can attack here, because we have dipole here, make bond here, and move these up onto oxygen to give that oxygen its second lone pair. And finally, we have what's called ozonide. That's called a malozonide. I don't know how to spell, but what does mal mean? Bad. Muy mal. See? Yeah? Si muchas veces vamos a la escuela los sábados, ¿sí?
Espero que no.
¿Mm?
Espero que no.
Uh-huh, see? That's the only Spanish I know. I was in a play in 7th grade, and that was my line. I still remember. Okay, muy mal. It's a bad ozonide. Bad ozonides are unstable. They rearrange by this pretty involved, lots going on here, you know? Ultimately, when you react ozone with an alkene, what do you get? You get an ozonide. It's stable. It can be isolated. It's a 5-membered ring, but it doesn't have 3 oxygens all bonded like the bad ozonides. It only has 2 bonded together. The other one is no longer bonded to those 2. All right? But now if you come in with some other reagent, and I'm just going to call it magic, now you can do the magic. I'm not going to show mechanism for this. And you can get the 2 products. One thing you might say is, hey, this has 3 oxygens, there's only 2 in the products. Well, that's because if you use zinc, you make zinc oxide. That's the fate of the other oxygen. If you use dimethyl sulfide, you get DMSO, which, remember, where have we seen DMSO before?
Is it a solvent?
In a Mars solvent, but deuterated. This is, the sulfur becomes oxidized here. Thus, that's a reducing agent because it becomes oxidized. It's reducing. Again, we're not going to look at mechanism, I'm just calling it magic. It's an involved process. Remember, you got 2 looks at this, just sort of the predictive product. Ozonolysis with a magic step, what does that do to an alkene?
Cleaves it.
Cleaves it, and each carbon becomes?
Carbonyl.
There you go. Then the next layer is your mechanistic knowledge. Okay. There's a couple of questions in the workbook about how you might get some odd things. Choice of solvent. Importantly, though, aldehyde survives. At this point, why wouldn't it? Now, you can try those up there on your own. We'll look at them on Monday. I think we have time to finish up.
Dr. Stevens?
No, we're okay. We got 10 minutes.
Does this ozonolysis always make a ketone and an aldehyde?
No, just it depends on what's on the carbons.
Okay.
In my example, we gave a ketone and an aldehyde because one carbon had 2 R groups, and the other carbon only had 1 R group. All right. Why don't you just take ethylene and do ozonolysis? Sometimes we can do that, implying that you got to have a magic step. Okay. Well, maybe not. Sometimes we apply. You know, what would this give? Simplest alkene possible. Product.
2 carbon monoxide?
Not carbon monoxide. You just cleave this. Each carbon becomes carbonyl. But what's on the carbon? 2 H's. Each carbon has an H, right? There's your product. Why am I only showing 1 product? I thought this reaction gave 2 products.
Same.
Well, it's the same thing, so I'm only showing it once. You would not say 2 products here if it's the same thing. Right? There's the simplest ozonolysis reaction possible. It's going to give formaldehyde. That's called formaldehyde because 1 carbon is formic acid. We'll learn that going forward. Okay, aldehydes survive. But look at this. Remember KMNO4? What does KMNO4 do to an alkene?
Sin or aldehyde.
Alkene KMNO4, that's how we originally made the
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 diol?
diol. But then we said osmium tetroxide gives better yield. That's because KMNO4, if you don't do it right, you get other chemistry. What do you get? This chemistry. Okay? If you do KMNO4 with harsh conditions or make it acidic, KMNO4 is a stronger oxidant under acidic conditions. What you will get is you'll cleave the carbons. You won't just get the diol. By the way, you may get the diol, but can diols be cleaved? Yes. KMNO4 with harsh conditions will go all the way and cleave it, and you'll get the ozonolysis outcome. Okay? If you do ozonolysis, what do you get? This aldehyde and that ketone, because there is an H there. If you do KMNO4 harsh conditions, you get the same thing. The difference is, hold on, that's an aldehyde. Will KMNO4 do anything to aldehydes?
It makes carboxylic.
It's the big three. Remember the big three? Aldehydes don't survive with the big three. This is not going to survive with KMNO4. What will it be converted to? Just gets oxidized. Aldehydes are further oxidized with KMNO4. The beauty of ozonolysis is, as I said on the previous page, aldehydes do survive ozonolysis. As long as you use the two magic steps I showed you. You may see an ozonolysis reaction out there somewhere. I mean, you're going out this weekend, right? You may see an ozonolysis reaction out there somewhere where they got an acid as a product. But I guarantee you that's because their magic step had some type of oxidant in there. And they just oxidized their aldehyde at the same time. But if you do your magic step with zinc or dimethyl sulfide, aldehydes will survive. Okay? So, KMNO4 can do something. That's why KMNO4 doesn't give good yields of the diol, because this tends to happen as well. And so osmium tetroxide became used more for that reaction. Okay. To me, these alkene reactions are the most sort of memorization that we will ever do. I like to rely purely on mechanism. Like SN2, mechanism be your guide. These alkene reactions, you just have to kind of know what they do. Okay? And I promise you, going forward, we'll go back to mechanism. All right? I showed you some mechanism. The malosonide, ozonide is a mechanism that's worth looking at. I give you a couple of questions in the workbook that kind of play on that. Okay? But these reactions are just sort of outcomes. What is the outcome here? And again, the ozonolysis is a top 10 reaction in organic chemistry. A couple of things over there. These types of things in my handouts, I mentioned Organic 1, you guys do to me. I give you a lot of little applications. We don't always have time in class to talk about them. Okay? You just have to trust me that I think they're important enough to give you, and expect you to kind of be reading. As long as you're interested. And if you're not interested, then I'm not sure exactly why you're here. Question?
I was just wondering, would you want us to know the actual mechanism for the
Well, the general answer is yes. Yeah. Okay. Let's see how we're finishing up today. Okay, Monday. We'll go back and hit, I'm thinking, some multi-step synthesis with the oxides. There was a page where I gave you 4 or 5 structures to synthesize. Okay, we did one in class. The very first one was a carboxylic acid. Do you know any ways to make carboxylic acids now? Yes. The most straightforward is from a primary alcohol. So you can back that one up to an alcohol. And then you ask, well, how do I make the alcohol? All right? So it's functional group transformations. And this becomes your toolbox. How do you do things? Your knowledge you have in your toolbox to use. And a lot of organic, including organic 2, is functional group transformation. We just converted an alkene to carbonyl compound. One functional group to another. All right. Okay, guys. See some of you in lab this afternoon. Again, we'll see if we do an NMR lecture. All right. If you want to talk about NMR, you obviously need to bring your NMR materials and your questions, etc. So we can do that while the reaction stirs.